When examining sample means, as we have been with our t-tests, a useful statistical tool is the confidence interval, which we, for example, often see associated with polling results when there's an upcoming election. Confidence intervals allow us to make statements such as, there is a 95% chance that the population mean lies within this particular range of values. We can calculate a confidence interval by rearranging the z-score formula. Let's have a look. All right, so recalling this z-score formula, we can rearrange it, just move some terms around using algebra to get the confidence interval formula. So the confidence interval formula looks like this. So we have x bar, our sample mean that we're now very familiar with, and then it's plus and minus. So our confidence interval has to have a top end and a bottom end. So the plus minus symbol lets us have both. So our sample mean plus n minus z times the sample standard deviation divided by the square root of n, where n is the sample size as we've come accustomed to calling it. So most of these values are very familiar. X bar is the sample mean, S is the sample standard deviation, n is the sample size. But what about the z value? What z value should we use? So this corresponds to a particular z-score threshold. So earlier in this notebook, we calculated the most common 95% confidence interval threshold. So that corresponds to that alpha value of 0.05, that p-value of 0.05 that is our significance threshold. So that's the most common one. And as we calculated earlier in this notebook, that corresponds to a z of plus n minus 1.96. Other popular ones are the 90% confidence interval at z is equal to 1.6 and the 99% at z is equal to 2.6. So the more important it is that your estimate is accurate, the higher the percentage confidence interval that you want to use. For example, using the 95% confidence interval to find the true mean yield of our GMO yeast, we can take our 8 GMO yeast values from the recent exercise, put those into a NumPy array, so we have a vector tensor called x, and then we can calculate x bar, that's the mean. We can calculate the standard deviation of the sample, that's s, and n is just the number of observations in the sample. So there we go, we've got those, and then we're going to use that z threshold of plus or minus 1.96. And now we have everything we need. So I created this little function here, the confidence interval error calculator. So it's just the formula that we have up here. And the reason why I'm calling it the confidence interval error calculator will become obvious in a minute, because when I pass in the z, s, and n values that we calculated here, that gives me my error. So it tells me how far from x bar our confidence intervals are going to be. And then I can add that error to the mean, to x bar, or subtract it from the bar to give me my full confidence interval around the mean of these values. So we could say that, therefore, there's a 95% chance that the true mean yield, so the underlying true value of GMO yeast, is that it produces a yield in the range of 51.2 up to 58.1 liters. And so we know what our sample mean is, right? So the whole point of this confidence interval is that it's trivially easy to calculate a sample mean because we have our sample. That's a piece of cake. But what we're trying to do here is estimate the true mean underlying it. So when you poll a bunch of people before an election and you want to know how they're really going to vote, that sample gives you an estimate of how the real underlying population is going to vote. So our sample gives us an estimate of what the real GMO yeast population yield is. And so based on our sample, we can say there's a 95% chance that the true mean is somewhere between 51.2 and 58.1 liters. Now, one thing to note here is that since this confidence interval doesn't overlap with the established baseline of 50 liters of yield for our non-GMO yeast, this corresponds to stating that the GMO yield is significantly greater, statistically significantly greater, than the baseline where alpha is equal to 0.05. So you can see this relationship between that 0.05 threshold, that probability threshold, and that 95% chance that we're using in our terminology for the confidence interval. And let's put all of this in a nice chart just for fun. So we're using some Matplotlib here. So we can see that this is the baseline for our non-GMO yeast that we're typically using in our brewery. And then here is the mean yield of our new GMO strain. And these are the confidence interval bars. So you can use the error bar method here in Matplotlib to get those. You simply pass in the confidence interval error values that correspond to the mean value. So typically we would have multiple points in here. So you could have a list of means and corresponding confidence interval errors, and that would give you a few points, each of which would have its own confidence interval error bars around it. And in fact, let's look at an example of multiple confidence interval errors in a single plot right now. So in the same way that we can compare a single sample with a reference mean using the single sample t-test, we can also compare multiple samples using independent or paired t-tests. So let's right now compare several sample means with confidence intervals. So we'll use our penguins again. And so we can use our confidence interval error calculator yet again, pass in the z-value of interest, that 1.96 z-value corresponding to the 95% confidence threshold, and then the standard error for the female penguins, the standard error for the male penguins, and the number of female penguins and the number of male penguins. So these are using variables that we created earlier in the notebook. And then we can plot them out. So we pass in our list of means. So F bar, the female average weight, the male average weight, M bar, and then the confidence intervals. And as you can see here, there's absolutely no overlap between the two confidence intervals, which indicates that this is a statistically significant difference. And we actually calculated earlier that this had an extremely significant difference. So the negative log p-value was about 25. And so yes, definitely a statistically significant difference. In contrast, if we look at the confidence intervals for female penguins from the three different islands, Torgerson, Biscoe, and Dream, so let's create those three vectors of weights, and then we can calculate the means for each of those three vectors, as well as the standard errors for each of the three vectors. I had to use S_t here to disambiguate from the stats package, which we imported at the top of this notebook, and also the number of observations in each of the three groups. So Torgerson, Biscoe, Dream, the means of them, standard errors, the count of observations, and with those values, I can use my confidence interval error calculator to pass in the correct z, standard error, and count for each of the three groups, the T group, the B group, and the D group. The z is always the same, right? That's our 1.96, corresponding to the 95% confidence interval. And then we can plot out the error bars. So I have my means in a list, I have my confidence intervals in a list, and so I can add those as arguments into my error bar plot. And voila, we see that definitely there's no statistically significant difference between the Biscoe female Adelie penguins versus Torgerson and Dream. And it looks like there might be, like just barely, Torgerson doesn't overlap with Dream. So you might want to separately test that in a t-test, but it does look like they do not overlap, which suggests that there is a statistically significant difference in weight between the Torgerson and Dream islands. Nice, so one last topic for you on the comparison of mean front, and that is to allow us to compare these three groups against each other simultaneously. So everything we've been doing so far with t-tests allows us to compare one group against another group. But what if we have multiple groups that we'd like to compare? Well, we can do that with analysis of variance. That's coming up next.